Let's get started for the afternoon session. So we're happy to have Andrei talking about topological heavy fermions.
Okay, thanks a lot, and thanks for the invitation. It's great to be back in Santa Barbara after a long absence. What I wanted to talk about today has been basically work done by Dumitru, Jonah, Hawaii, and Jabin, and none of it would have been possible without many talks and consultations and collaborations with people that you see, more senior people that you see in this role. So this talk is about what happens when you add interactions to flat bands, and I'll particularize to twisted bilayer, but towards the end we'll show you that it's not necessary to do this, and we'll point out other systems where the principle that I want to introduce applies. But there's two cases that basically the way I think about flat bands interactions that you can separate the problem into, and this is a case that I won't be looking at. And this case is the case where I have a flat band and the energy gap to the dispersive band is large. Here is put it to be infinity. And large meaning larger than the interaction scale. In this case, basically, you can just kind of, if you're at fillings of this, partial fillings of this lower band, you can basically project your interaction to this lower band and consider a projected Hamiltonian with the interaction projected in this band. Now, this projected Hamiltonian basically has nice properties. It turns out you can sort of define some positive semi-definiteness, etc. And for example, you have some remarkable properties. I think that the collective mode spectrum, for example, stiffness, is basically given by the Fubini's 2D metric. This is the mass tensor here. So kind of like the quantum geometric properties of the band, and these are exact calculations for certain models. The models don't become exactly solvable fully, but you can solve for the ground state and some excitations above the ground states in some cases. And you find out the quantum geometric tensor and the Fubini's 2D metric kind of naturally come in. But this is not the case that I'll be talking about. And for these cases, you can basically look at Päivi Torma's papers with Kuka, Jonah, Dumitru, and Aaron. But the case that I'll be talking about is the other case where the gap between the flat band and the dispersive bands is not much larger than the interaction. For example, such cases occur naturally, for example, on the Lieb lattice, where you have a Dirac point connecting the flat band and the dispersive bands, and in many other cases, including twisted bilayer graphene, which I'll particularize to. And in twisted bilayer graphene, just to introduce the system, of course, everybody knows about it. You just take two layers of graphene, you twist them, and you twist them at a small angle, and you get flat bands. And in this case, the gap from the flat bands to the dispersive bands is, of the order, sometimes depending on what regime you are, less sometimes, of the order of the interaction. So you can't really neglect it, at least, a priori. You can sometimes project it or try to project and compare results. But I'd like to give a principle that doesn't neglect these other bands, and this, of course, will become necessary for splits, line graph lattices, etc., such as Lieb. So, as I said, you take two layers of graphene, you rotate them a little bit, and what you get is 2 bands per valley per spin, which you can fill from -4 electrons to 4 electrons. So this is kind of the convention. And this is the model, the celebrated continuum model. In this particular case, is the Vista-McDonald model, which has extra symmetries that I'll be pointing out. And you see the phase diagram where if I go from -4 to 4 electrons, the system is a single particle metal, but it's a many-body insulator at integer filling, and you've got superconductivity in between these integer fillings. Now, by now there's many experiments on this system, and the experiments kind of point to a structure of the system which has both localized and itinerant electrons. So, for example, this is some STM experiments. This particular one is Ali's group, where you basically see localized charges. You basically see Coulomb blockade physics, large Hubbard U on the triangular lattice here of the Moire scale. And of course, there are the experiments from Andrei Young and Shahal Ilani's groups where they see loosely coupled local moments by doing spin entropy, etc. So these point to the existence of local moments. But then, of course, there's many other experiments which point to the existence of itinerant states. So this is from the abstract of a paper in the field that says that the correlated states in the system feature seemingly contradictory properties associated with itinerant electrons and localized moments. So in this sense, you could kind of argue that the system looks like a heavy fermion system where you've got some localized heavy states and some delocalized electrons. The problem, however, is that the flat bands that I was showing you, or flattish bands that I was showing you before, are topological. So you cannot build fully localized states out of them. So now I want to basically introduce what we claim is sort of a principle that transcends twisted bilayer, that applies also to the Lieb lattice, as I'll show later in twisted checkerboard and other lattices. And that deals with interactions when in flat bands, when you've got the interactions that are stronger than the dispersion between the flat bands and the gap between the flat bands and the dispersive bands. And this principle goes as follows. So what we're interested in is obviously flat bands that are, either topological or have quantum geometry. We're not interested in really flat bands that are just localized electrons with no hopping, right? And it turns out that you can sort of prove that exact flat bands that come basically from quantum interference, meaning from hoppings that are non-zero, that are large, but you still get some flat bands in the system. That flat bands that come from finite hopping are likely to be topological. It's not always the case, and you can kind of characterize when is the case, when it's not the case, but they're likely to be topological. So that means that basically you cannot find a localized description for them, even though if you respect the symmetries of the system. Now, however, we know how topology happens, right? We've had lots of experience in how topology arises. And topology arises basically through band inversion in a lot of systems, right? And if it arises through band inversions in lattice systems, unlike in Landau levels, then the Berry curvature, or some non-abelian variant of it, or you can define some metric for these, is concentrated where the inversion took place. For example, in twisted bilayer graphene, some non-abelian variant of the Berry curvature, the trace is zero, but this some non-abelian variant, is actually concentrated at the gamma point. Doesn't have anything to do with these flat bands, doesn't have anything to do with the K point, it's concentrated at the gamma point. And the reason for that is that that's where the representations actually don't match the ones that would be necessary to get an atomic limit. So if I have the Berry curvature or the non-abelian variant to be concentrated at the gamma point, or at some point where the band inversion took place in order for the band to become topological, then in a lot of other places of the Brillouin zone, I have no Berry curvature. This is very unlike the Landau level. And it means that basically, if I just concentrated in these other areas, I could form localized states. The only problem is where the inversion took place, I can't form localized states. away from these hotspots, basically the band can be sort of linearized. Now, of course, since topological, it can't be fully linearized. But what we want to do, as in all examples of physics, is to find basically a good basis to describe the physics. And what we claim is that this good basis is basically that of localized orbitals, which are almost good in the entire Brillouin zone except for these hotspots, and that of metals. In this case, it would be a topological semi-metal, which basically kind of takes care of the topology. So we kind of want to pawn off the topology of the flat bands into the topology of a semi-metal, which, when coupled to localized states, gives you these topological flat bands. So we want to think of the topological flat band as some trivially localized flat band, which now basically carries the interaction, okay? Because we'll see, because of their localization properties, these carry these heavy states, which we call them heavy fermions or F states, by abuse of language, carry most of the interaction. And these are Vanier states that are exponentially localized. And they're coupled to a topological semi-metal, which carries the topology. And I'll show you at the end that, for example, Jabin and Jonah basically figured out that the same principle applies to the Lieb lattice, to the twisted checkerboard lattice, etc. And that's the single particle part. But now that you have made basically this unitary rotation to degrees of freedom that are physical, you know which one carries the interaction. And these are the F electrons. And you can write an interacting model. And the interacting model is almost generically some new type of Anderson and Kondo models, which are basically, we call them Anderson plus, because they have extra terms besides the Anderson, the regular Anderson model. So I want to go through this. So this is going to get you a bit deeper into the twisted bilayer graphene theory. But basically what happens, all you need to know, is that in the Moiré-Brillouin zone, these continuum models, which were developed by several people, but the most famous of which is, of course, Vista-McDonald model, gives you these flat bands, 2 per value per spin. And these are some representation labels of the flat bands at high symmetry points. Now, you can go on this website, which is now available to just for your browsing enjoyment, and find out that these representations are not consistent to any atomic limit, with any atomic limit. Hence, these bands are topological. And we can understand the topology in many ways, but it turns out that in this Vista-McDonald model, the topology is actually strong. It's a continuum model, which means that at any bandwidth, this model does not have a lattice representation if you keep the symmetries of this model, in particular particle Hall, which will be broken later, and this is some new stuff that I'm going to present today. But basically, these topology of these bands, or any bands at finite bandwidth, is equivalent to having 4n plus 2 Dirac points in an energy window E minus E. So not 4n plus 2. This is similar to the surface of a topological insulator, except this is the surface of nothing, and it's just a bulk, and you've got, instead of an odd number of Dirac points, you have an even number of Dirac points. The symmetry allows for this type of a strong topology. Now, this topology basically forbids short lattice models with any finite number of bands if you want to model the Vista-McDonald Hamiltonian. So just remember this 4n plus 2 because it will become important in the next slide. So we know from experiments roughly that the system has to be heavy, has to have heavy carriers and light carriers. So let's try to build the heavy carriers. And what you notice is that these flat bands here, well, first of all, I showed you their non-abelian Berry curvatures at the gamma point. But consistent with this is the fact that these representations at the gamma point are the wrong ones for an atomic limit. In particular, if I change these two one-dimensional representation to a gamma 3 representation, which is a two-dimensional representation, if I just borrow that, we can build an atomic limit. And this atomic limit is actually on the triangular lattice. And you immediately look and you see that there are these gamma 3 representations in the dispersive bands immediately up there. There's actually two of them, okay, one above, one below. So we just borrow one of them, okay, and with one of them, if I just replace this gamma 1, gamma 2 by gamma 3, I would get an atomic limit. I would be able to write down an atomic limit of these bands, and it would be a px plus minus IPY orbital, which again by abusive language we'll call it an F orbital, at the 1a Wyckoff position, which is a triangular lattice. So what you do is you take an energy window of basically plus minus u, and you build trial states, and then you run them through Vanya 90 and find the maximum localized states. And it turns out that the maximum localized states, the maximum localization is roughly 0.2 the Moire lattice. So this means that these heavy states from one Moire lattice to the other basically don't hop to each other. So the Hamiltonian of the heavy states is 0. Okay, it's exactly flat band. Basically, hopping between them is 0.1 milli-electron volts. If you're going to compute it, you just put it to 0. And then you ask how much of these flat bands are made out of these Vanya states. You know it cannot be 100% because the representations at the gamma point don't match. And what you find out is that roughly 96% of the bands of these flat bands are contributed by these localized Vanya states. Okay, so most of these flat bands are localized, and 4% of them is basically delocalized. So let's build that 4%. And this 4% is very easy to build because we know that at the gamma point we have 6 bands per value per spin, and we've used one of these gamma 3 representations to build the Vanya state. So the leftover representations at the gamma point is gamma 1, gamma 2, and another gamma 3. So it's a 2-dimensional and 2 1-dimensional representation, 1 2-dimensional. And you can do symmetry analysis, or you can just brute force calculate it. And what you find out is that the conduction electrons, or the light particles, are exactly those of an untwisted AB Bernal stacking, where I have a double vortex here, and this double vortex reminds you of the 4n plus 2 Dirac fermions. You basically solve the anomaly by just by pawning off the topology onto the double vortex, which is equivalent to 2 Diracs. And these gamma 1 and gamma 2 representations are just the next bands. Of course, this energy here is now just the bandwidth of the Bister-McDonald. It's not like in Bernal graphene, 110 milli-electron volts. It's just very small. So the difference of energy between the gamma 1 and gamma 2 representation is just the bandwidth of twisted bilayer graphene. But this looks exactly like an AB untwisted bilayer, and the Hamiltonian for it basically proves this. So this you can obtain from symmetry arguments. Of course, these velocities you have to obtain them from the actual continuum model from microscopics, and this is what we obtain. So this m is the bandwidth of the Bister-McDonald model, or twice times m is the bandwidth of the Bister-McDonald model. It basically opens up this gap between gamma 1 and gamma 2 representation, single dimensional representation, and there's a twofold representation here which carries a double vortex, and there's a linear combination, there's a linear in momentum Hamiltonian between them. So now we have the light electrons. We took care of the topology. We have the heavy electrons, but how do we get to the actual continuum model bands? Well, that's easy. You just have to get the coupling between the heavy and light electrons. And this is particularly easy in some limit, where you just consider the first order. Of course, you can add extra terms, but the heavy electrons have a gamma 3 representation at the gamma point. The light electrons also have a gamma 3 at the gamma point, so their coupling is just a constant. And this constant is actually the gap, which you call gamma, becomes the gap between the flat bands and the dispersive bands. Okay, so this is by now the larger energy scale in the problem is 24 milli-electron volts, something like this. Of course, this depends on the details of the model. So now we have a very simple representation of the Bister-McDonald Hamiltonian, of the continuum Hamiltonian, which is this at its most basic level. And this representation is basically here is the F electrons, the heavy electrons. They couple to only the gamma 3 of the light electrons to the double vortex through this gamma, and then there's a double vortex Hamiltonian here, plus this is the AB untwisted bilayer Hamiltonian, this 4x4. These are the light electrons. And you can ask, how well does this approximate a continuum model? And this is how well it does in some energy window of plus minus the interaction. You can see that basically the red dots are the Bicester-McDonald model and the black lines are this model. So you can see that it does particularly well. Now, for reasons that I'll get back to later, and because I get this question a lot in talks, the Bicester-McDonald model, as I said, has a particular symmetry, which is an extra symmetry, which is particle Hall, which, if you look at the ab initio done by, Caxiras and Coscino, etc., you don't find it or you find it, if you look at the spectrum, it doesn't look exactly particle Hall symmetric. Okay, so in particular, this is how the spectrum looks, and this is a particularly nice representation of the spectrum obtained by Kang and Vafek, which basically adds terms that look kind of like this. There's a sort of a gauge potential term, and there's some other terms in this interlayer coupling, and there's some extra terms. And these terms are more than the terms that have been considered in recent Hamiltonians. So there's a lot of terms in these very nice Kang and Vafek papers that basically give you the continuum description, and this is how it looks, okay, as opposed to this. Okay, so there's some differences, but if you look at how much the particle Hall is broken, there's, most of the, we call this the Kang-Vafek model, most of the system is still particle Hall symmetric. There's about 10 to 15% particle Hall symmetry broken on a ring here. At the gamma point is still very much particle Hall symmetric, and there's particle Hall symmetry here. So what you can do is you can build a heavy fermion model of this Hamiltonian, and this is what Jonah, Jabin, Dimitri, and Howie did in the past basically week, and ask, how well does this model fit the realistic band structure? And this is how well it fits. There's the gray and the blue are one or the other model. The gray is the Kang and Vafek model. So you see it fits remarkably well within plus minus Hubbard U. And again, the localization, there's still heavy fermions. There's 90 more, I think it's 97% overlap or something like this. And the only extra thing that you need to add to the heavy fermion Hamiltonian is a chemical potential for the F electrons, a chemical potential for the C electrons, and some linear terms. So all these extra Kang and Vafek terms that are shown here become particularly simple in this heavy fermion model. You just add some chemical potentials and some linear terms. Now, it also turns out that for most practical purposes, the heavy fermion states are still particle Hall symmetric. As I showed you, most of these, the particle Hall symmetry breaking is a lot in the energy, at most 15% in the wave function on this ring, but in a lot of the Briand zone, there's not much particle Hall symmetry breaking. So in particular, it's the wave functions, not the energy, of the heavy fermions can still be considered particle Hall symmetric, and this was a realization that Jonah, Jabin, Dimitri, and Howie did in the past week. So I just wanted to show you this because this is a recurring question. You can add these particle Hall symmetry breaking terms and get heavy fermion Hamiltonian that's almost as easy as the original one. So now we have this non-interacting Hamiltonian that we basically separate into degrees of freedom. And you'd expect that the degrees of freedom that are heavy will carry the interaction. So you can actually compute the interaction by just projecting the Coulomb interaction, screened Coulomb, to this basis. And what you find is, as expected, that basically most of the interaction comes as a Hubbard U of the heavy fermions. This is normal ordered, and the Hubbard U here is 57 meter. You know, in STM experiments, U1/2 is quoted, etc. These values can change depending on the angle. Okay, and there's another term, which is why we call these models Anderson plus models. There's other terms that basically looks kind of ugly, but whose interpretation will be given in the next slide, and it's not that ugly. And in particular, U1, this Hubbard U, is the main source of symmetry breaking. You basically want to polarize these F electrons at integer fillings to lower the energy. Now, in the original paper, we obtained these values, U and J and all these other values, by just projecting, you know, numerically by projecting the continuum model. But it turns out you can do an analytic job and obtain these values as a function of parameters that are called W0 and W1 for the experts in the field. So this J term will turn out to be a ferromagnetic coupling between some larger symmetry moments. And these are the larger symmetry moments. Now, it turns out that in projected Hamiltonians, so when you took your Coulomb interaction and projected to the flat bands, okay, there was a large symmetry discovered, okay, starting with Kang-Waffe, Bultnik, and others, basically, and this symmetry was some large U4 manifold, and in some limits it was U4 times U4, etc. In this model, actually, this symmetry is true even without projection. So it actually commutes with the kinetic term, which is not true for the if I just take the Bister-McDonald model, that's and add extra bands, that's not true in these. This is a symmetry for the projected Hamiltonian. In this heavy fermion model, due to some extra symmetry, in some limit, which we call the flat limit, which is not for the experts equal to the chiral limit. In the flat limit, you have a U4 symmetry of the full Hamiltonian, which is basically, we characterize it as the same as the projected U4 of these projected Hamiltonians. And in this limit, you can write down the 2 F electrons per valley per spin as 2 U4 spins. And this J interaction that existed in the Anderson plus model becomes a particularly nice interaction in this form. It's just the interaction between the F electron U4 spins and the C electron U4 spins with a ferromagnetic coupling here. Now, without this J and without the hybridization term, the model is exactly solvable. So without the gamma term that hybridizes the F and C electrons, the one-body term, the model is exactly solvable. And in this model, you can immediately see that the filling is clearly controlled by the F electrons. So at integer filling, you want to fill an integer number of these F electrons, except at nu equals plus minus 3, where you have somewhat of a degeneracy between filling 2 F electrons and 1 C electron and filling 3 F electrons. So there you have charge fluctuations, and this is kind of consistent with lack of gaps at this filling for non-aligned samples. Now, I wanted to point out that similar results are obtained by other methods, and a small part of the authors that have obtained them are listed here. Now, as I said, the filling is at integer. It's basically filling the F electrons because you want to minimize their Hubbard U. But you can ask, how do you fill them? And it turns out, and this is something that was found by Hao Yu, that basically you can prove analytically that there's a Hund's rule coupling between these F electrons. So these F electrons basically want a Hund's rule couple, and you want to form the largest symmetric, well, the symmetric representation of the U4 moments. So what we do to obtain the correlated states at integer filling, I'll come back to this later, is, for example, at 0 at charge neutrality, you just fill 4 of these F electrons times the Fermi C of this quadratic touching of this AB double Dirac node, and you've put these in a U4 symmetric representation. Now you can rotate it around in the limit m equals to 0, and these give you the general states. That splits when you put in a little bit of bandwidth of the bands, and which state wins we'll see here. This is again for the symmetric, particle hole symmetric Bissell McDonald model. As I said, you can add these extra terms and fit the ab initio with the heavy fermions. So in this particular representation, these insulators at integer filling are very easy to understand. All you do, for example, at 0 filling, you just fill up 4 f electrons. They move up and down the bands. Now this is with Fc coupling turned off and with the ferromagnetic J between the U4 of the F electrons and U4 of the C electrons turned off. Two things happen. If you turn on the Fc hybridization, you won't obtain, you'll obtain avoided crossings here, which you can see here. And if you turn on J, or the ferromagnetic coupling between F and C electrons, you'll basically, because of the order parameter of the F electrons, you'll basically open a gap in this double vortex. Now, because you open a gap in the double vortex, you're going to get some Hall conductance, and whether the state has any Hall conductance, an overall Hall conductance, depends on how different, valleys and spins add up. Now, I want to point out that this is for unstrained clean samples, and I think Nick will tell us about what happens in strain samples. And I want to point out that the prediction, and this is something that comes out of a lot of models, is that the KVC state, which is some particular state, wins. Now, the issue with that is that that doesn't seem to be confirmed by experiments. So this is experiments from Ali Yazdani that we were involved in, and basically was early on found by Dumitru and by Hong in Mike Zartel's group, that basically KVC, even though it contains intervalley components, doesn't show what we call an R3 pattern or a pattern at this large momentum because of an extra symmetry of the state. It's a little bit subtle, but it doesn't show it, whereas the experiments do show it. And this, in the clean or cleaner samples, are consistent with another state, which is TIVC, which is not the KIVC state. However, what I want to point out is that these TIVC and KIVC states, they're part of this low energy manifold. They're split only by a little bit. So we're currently investigating whether these extra terms, this particle hole symmetry breaking terms, can give you this state without, extra input. Probably we'll hear about some of this extra input in the next talk, such as electron phonon coupling. So there's still work that's under investigation. Now, just to end, because I've overstayed my time, basically, same thing can be done for tri-layers. This is Jabin's work, and it gives you a nice way of understanding, obviously, the states. But the last thing that I wanted to point out, as I promised at the very beginning, is that this seems to be as I argued at the very beginning, that this is kind of a general procedure. So, for example, if I take the checkerball model and twist two checkerball lattices, as Hong Yao and collaborators did in this paper, what we find is another flat band with other topological states, topological sets of flat bands. But again, the Berry curvature is at these points. We can again, by the argument that I gave, separate the model into heavy and light particles, and you can see how much of these bands are heavy particles given by the size of these dots, and how much are light particles. Moreover, for the Lie lattice, in which case you cannot basically have you cannot project to the flat band because you've got this gapless point here. You can do exactly the same procedure, and the results are also extremely interesting. This is most of this Lieb flat band is actually heavy fermions, as you can see here. And these heavy fermions are now actually located at a position in the lattice where there's no atom. So they're kind of what we call an obstructed atomic limit. So they're located at the center of the lattice where there's no atom. And you've got some Dirac fermions that pick up basically kind of the topology of the model. Okay, so this is my the end of my slides. And you can read this, or I can take questions on what I meant here. Thank you.
All right. Thank you for the nice talk. So, any questions?
So do I understand correctly that you put gamma 3, you have the same gamma 3 representation in both your heavy and your light electrons?
The gamma 3 representations are in the Bicester-McDonald model. They're representations of the dispersive bands. Okay. Now, what you do is you cannot build localized states without having the gamma 3 representation be. So one gamma 3 is that of the F electrons, and the other one is the double vortex, is this guy. So one is this gamma 3, and one is the F electrons.
Right, so aren't you double counting in a way?
No, because I have two representations.
Oh.
Right, so I have one gamma 3 and another gamma 3.
I see.
And that's the, so this is the faithful, you don't lose any of the symmetries, you respect everything is kosher. So you have two gamma 3s, and you're using one of them to build the F electrons, which are the whatever px plus minus ipy on the triangular lattice, and the other gamma 3 comes from the double vortex, which carries the topology. This is the 4n plus 2 Dirac fermions.
Okay.
Does it make sense?
Yeah. So I was also curious about your first statement that flat bands with finite hoppings are likely topological. What does that even mean?
That means that if you have a small number of flat bands, you can describe, and this is not only by representations, you can do it by real space indicators. You can describe the flat band as not a sum of atomic limits. It's a difference of atomic limits, and that's natural. That comes out of the bipartite, basically Lieb construction. All these flat bands are basically Lieb constructions in the end. Without particle hole symmetry, I think we think that that's an exhaustive, that all the flat bands would basically come to be a Lieb type construction. You know, the line graphs are basically a Lieb construction where you just add some massive term on some of the sites and you take them out of the spectrum, but they're all at their basis a Lieb construction. And for those, there's an argument to show that these flat bands are not, at least for small numbers, they naturally come not as sums of atomic limits. Now, it can happen that they are sums of atomic limits, but naturally they don't.
Okay, but
we can talk about this more. This is, I mean, this is a full different talk.
Okay, I mean, I think it's easier to come up with counterexamples. Right?
Of course, I'm not saying that they're always, but naturally they come out as not sums of atomic limits.
Thanks.
Hi, I wanted to, so in the beginning of the talk, you kind of showed two different perturbative frameworks, one where the interactions are much smaller than the band gap, and one where the interactions are much larger than the band gap. And as I understand it, this will lead to two different predictions for the occupations around the gamma point. For example, if the interactions are much larger than the band gap, you said you occupy the F electron states. But instead, if the interactions were much less than the band gap, you would occupy the hybridized states. So that lets you kind of do a quantitative test where you can test how much band projection fails. You can do self-consistent Hartree-Fock, and you can look at how much the occupations of the remote bands differ from
That's right.
0 and 1.
That's right.
Have you done this in the topological heavy fermion model? And
okay. Yeah. So that's a very good question. So first of all, I want to. Are you done? Are you done with the question?
Yeah.
Thanks. I don't want to interrupt you if you're not done. But yeah, that's a very good question. So the issue. So first of all, I want to point out that, for example, for graphene is, you know, you can do this calculation for twisted bilayer. But if I wanted to do it for the Lieb,
I agree.
Right, there's all these lattices where it's just not possible to project.
No, I agree.
Right?
I think it's a really great conceptual framework that can probably be. I'm just asking about.
Thank you. So basically, for that's something that So for example, this type of this is the charge 1 excitation above a ferromagnetic state, okay, computed from this heavy fermion. Now, there's papers, and there were actually there's actually papers here, or where this can also be computed by projection. And what you find by projection is that you just basically looks very similar. Maybe there's differences in bandwidth, etc., but it looks very similar to these first bands here, just these two. If I just took the projected Hamiltonian. Now, there are differences. So for example, the projected Hamiltonian in some limit gives you a larger degeneracy that's not supported by symmetry. It's kind of a fake degeneracy. They're exact states. For example, at nu = 0 in the chiral limit, the projected Hamiltonian gives you that the Chern number 0, 2, and 4 states are degenerate. That's a fake symmetry because there's nothing that makes it degenerate. But the heavy fermion model breaks that degeneracy.
I see.
Okay, and gives you the Chern number 0 to be
I see.
So there are differences. Now, I'm not claiming that they're huge in this. For example, that still remains to be seen. For example, like if I just take the Bisset-McDonald model, I can only stabilize the KAVC. The TAVC is very, it's competitive, but it's above. Now, the claim is that if one claim that could be true is that if we take, the particle hole and more bands, I can stabilize the other one. That still remains to be seen. But here you basically have, a huge manifold of states that are very low in energy, and extra bands could matter. So that's my answer. Also, for example, if you just project into the flat bands, you have a momentum representation of your interaction, etc. So for example, it wasn't understood why this is flat in the charge 1 spectrum from the projection. Okay, this part, you see, this is very flat. That's not understood from the projection because you just have a K representation, right? You just take your interaction, you project it, now it's all in momentum space. Here it's very easy to understand why it's flat because it just comes from the heavy fermions,
I thought it was because the form factors are approximately independent in K.
They're not independent, they're independent of K basically.
Yeah,
here.
Over there, not at gamma.
Right,
but
the reason for that is the heavy fermion, right? Because once you basically, physics is, all about choosing the right basis in a way. Right?
I think
so
I was asking something slightly different. I completely understand that if you take in the remote bands, that'll lift some degeneracies, and that's probably important. But and I agree that either using the heavy fermion model and basis, or using the BM basis and keeping remote bands, those are two different bases, but they're kind of motivated from two different perturbative schemes. One of which is U much larger than gamma, and the other is gamma much larger than U. And I'm wondering which one is, at least in these numerics, which one seems to be supported by the Hartree-Fock?
This one is U larger than gamma. So U is larger than gamma. So actually you can look in this paper and find where, once gamma becomes larger than U, it's the heavy fermion picture is useless because you're basically hybridizing the F and the C electrons so heavily that it doesn't make sense to think of them as separate.
So then I'm confused.
So around 1 point, for example, in the chiral limit, they become the gamma's larger, and then away from the magic angle, gamma becomes larger.
So I think I'm not talking about the bare parameters necessarily. I'm talking about the occupation of the remote bands.
Right. Okay. I don't know the answer to the exact occupation of the remote bands, but that's something that's calculable.
Yeah.
Right.
Okay.
So
you haven't done it.
We might have done it, but I might not remember it.
I see.
It's certainly somewhere there, right? It's a one-shot Hartree-Fock. You can actually solve it by hand, all this stuff. So it's very easy to get. This will basically tell you that if I do rigid filling, which is not correct, okay, these remote bands will start getting filled around here. Okay, so you can see the remote bands starting getting filled. Rigid filling is not correct. You shouldn't do rigid filling of these to go from 0 to 0.5. You're not going to rigidly fill the bands. But if you were to do that, they would start being filled at some point, right? So this is kind of fake answer to your question, but you kind of see that, right? Because these are flats, it doesn't take much to start filling these other bands.
You could just, I feel like you could make a really good support for having to do that heavy Fermion model if you show that there's more band.
Okay, thank you for the suggestion. We'll take it into consideration.
This is a much simpler question. So when you say the C electrons have to be in a semi-metal, so the statement is that you have to have a multidimensional representation, which is basically at the energy of where your flat bands would, the flat bands live. Is that the statement?
Yeah, so basically, so in this Bicester-McDonald model, which has particle hole symmetry, this is stuck to be a zero energy. Now I don't need to do that. So for example, I can add these extra terms which break particle hole symmetry, which, this is the two-dimensional representation. So it's a different energy, and so somehow, it doesn't, in this case, it doesn't look particle hole symmetric. It looks like this guy shifted a bit, and there's some other shift in between these and these. So, but yeah, this with particle hole symmetry, which is there in the Bicester-McDonald model, you'd have this fixed at zero, and these extra terms basically shift this up, and they change the one-dimensional representation shift relatively to the two-dimensional one.
And you could imagine doing a same construction, of course not for this model, but where you have your degenerate bands from the degenerate representation actually curve all in one direction, for example.
That's right. That's right. You can do that, but yeah. So you can do that, but we find that that would mean a lot of particle hole symmetry breaking, and the particle hole symmetry breaking is, it's considerable. But it's not as much as to bring everything. But I agree with you. You could do it to go in the same direction if you add some k-square terms. That's certainly true. But that's if you just compute the values of these terms based on the ab initio, you find them to be small. Very good, thanks.
So I know that there's quite a lot more questions, but I think we need to move on to the next talk. So let's thank the speaker again.